So welcome to today's Autonomy Talks. Today is my pleasure to welcome Professor Dario Paccagnan, who is a professor at the Department of Computing in Imperial College London since this fall, so it's a fresh position. So a bit of bio, Dario started obtaining his bachelor and master in aerospace engineering from the University of Padova. And he also got a master in mathematical modeling from the Technical University of Denmark. He then moved for his PhD next door to the Automatic Control Lab, where he obtained his PhD and also the ATH medal for the PhD. He then moved to better weather, to California, and he did his postdoc in University of California, Santa Barbara, and he then started as an assistant professor. Today we talk about the efficient operation of socio-technical systems with focus on optimal incentives for congestion games. And I'm really happy to let you the stage.
Thank you, everyone. Thanks for being here. It's a very great pleasure to be back with ETH, even though only virtually. As you can see from my title, my work centers around modeling and control of systems where human users interact with the underlying technological infrastructure. That's sort of the broader theme. And today's presentation would focus in particular on optimal incentives for atomic congestion games. Now, before starting with the presentation, let me just acknowledge my collaborators. Everything that I'm going to say today is joined to work together with Rahul and Bryce. They are two very strong PhD students in UC Santa Barbara, as well as with Jason Marden, who's one of my longest time collaborators. Now, in a broader sense than what I mentioned before, my interests are to some extent in multi-agent systems coordination. Now, I'm depicting these agents here purposely, this multi-agent system here purposely on the spectrum ranging from social systems on the left all the way to engineered systems on the right. Where the idea is that in social systems, the emergent behavior depends on how agents, in this case humans, socially interact with each other. While in the other extreme, there are engineered systems. These are systems where the resulting performance depends on how each and every component is designed and how its components are pieced together. Now, there's another class of problems, which I'm referring to as socio-technical system, this box here in between, which borrows properties from these two extreme classes. Now, while in the past I worked mainly on these two areas, today's presentation would focus heavily on socio-technical systems and in particular on the application of traffic routing. In a broader sense, the central goal of the research agenda is that of coordinating socio-technical systems to desirable behavior. And I hope this would be clear. I hope this theme would be clear by the end of the presentation. If this is not the case, please feel free to ask, and I'll be more than happy to try and see if I can better explain that. So what is a socio-technical system? Now, we can informally think of a socio-technical system as a system composed of two blocks. The first block is meant to describe the underlying infrastructure. Think, for example, at the road network, the inter-backbone, the power grid, for example. While the second block is utilized to model users' behavior. So how do human agents utilize the underlying infrastructure? And the key point, the key observation in socio-technical systems is that the resulting performance cannot be gauged by looking at any of these two blocks separately, but instead depends on the interplay between these two different components. And here you have one example of such performance. This is a traffic routing pattern in California. Now, as you can imagine, as you can see from this dramatic picture, oftentimes the emergent performance is undesirable. So the fundamental question that arises there then is, well, then how can we incentivize good performance? And this is somehow the higher level theme, and what computer scientists would often think about is something called mechanism. Now, control theorists are more familiar with the lingo of feedback loop. So the idea is particularly simple, is that of measuring current performance, feeding this to a mechanism where this mechanism produces incentives. And the idea is that to utilize these incentives to influence users' behavior so that the resulting performance at the end of the day would have improved. Now, clearly here I'm talking about socio-technical systems and I'm showing pictures about traffic routing, but the theme is more general. And as a matter of fact, socio-technical systems are pervasive. You can find plenty of them under the big umbrella of smart cities. Here you have some examples. And while socio-technical systems are pervasive, they also come with a very large number of associated challenges, mainly because of their interdisciplinary expertise that is required to understand subsystems, ranging from control to economics, urban planning. You really need a lot of ideas to put together. And what I'm trying to claim here is that as control theorists and computer scientists, we have a number of tools which we know, which are part of our tool bag, which we can utilize to answer some very interesting questions related to socio-technical systems. Now, this somehow gives you a brief overview on the research team, and I'm going to get slightly more specific. So I'm going to look at a special class of socio-technical systems. I'm going to talk about smart mobility systems. And in particular, the bulk of today's presentation will be about how to design optimal incentives, optimal mechanisms in congestion pricing, in congestion games. And the idea will be that of utilizing congestion pricing as a way to achieve that. Now, this is point number one. We'll cover, say, the next 20-25 minutes of the talk, so the main part of the talk. After that, we will take a step back and look at opportunities, both within the socio-technical system at large and within more specifically smart mobility problems. Now, having said that, I'm sure you're familiar with the picture like this. Congestion is in fact growing throughout the world. Not only congestion, but also the costs associated to congestion. And here I'm thinking about direct costs, for example, the time spent on the road, as well as indirect costs, such as, for example, greenhouse gas emissions, as you can see here, which amount to a large fraction of the overall greenhouse gas emission, that of transportation. At the same time, a number of solutions have been proposed to try and tackle this problem. And one of the most hyped, I would say, approaches these days is that of congestion pricing. Now, this is most likely because Manhattan, New York is already decided to roll out their own congestion pricing scheme, but also because a number of European cities are following the same lead, and other cities such as London or Singapore, for example, already have a congestion pricing scheme in place for a very large number of years, say at least 10, 15 years. So what is the issue with the current schemes? Well, the issue is that these are very simple schemes. They are often referred to as blunt policies. They are typically perimeter policies, meaning that we draw certain perimeters and all the cars that will enter such perimeter will have to pay a certain fixed toll. On the other hand, in the future, and perhaps already now, we will start to have more fine-grained and adaptive location data. And the idea there is, well, how can we exploit this location data? Can we do anything with it? And the fundamental question that sort of is overarching throughout this presentation is the following. Can we define fine-grained and adaptive congestion pricing utilizing this data? Can we move away from the sort of simple blunt policies to a more refined policy? And how can we do that? Now, I hope the question is clear. But before trying to answer the question, we need to understand what is the problem we are trying to solve by means of congestion pricing. So this is exactly what the next slide is meant to do. And it's a very simple slide, but it's extremely important that you try and follow me on this one, as somehow the whole approach will be introduced here informally. If at the end of the slide something is unclear, I'm going to wait for you, and please feel free to ask me here so that everything somehow we start on a good level for the next slide. So the fundamental issue here that we are trying to tackle is the following. Whenever agents are self-interested, the emergent performance could be much worse than that of a centralized imposed solution. And I would like to clarify this with one very simple, almost trivial example. So let us look at this very simple routing problem here. There are two agents. There's a red car and there's a blue car. Now, both agents would like to travel from a common origin to the left to a common destination on the right. And the idea is that their travel time depends on which path, which link they choose, right? They could either choose the top link, in which case the agent would incur a travel time of 2 units of time, let's say 2 minutes, for example. while transiting through the bottom link here, any agent would incur a cost that is proportional to the congestion in that same link. So to clarify, if one agent was to select this link, that agent would incur a travel time of 1 unit of time. If 2 agents were to select that link, both agents would incur a travel time of 2 units of time. Okay, so having said that, somehow the infrastructure is there, we need a model for user behavior. And what we're going to utilize here is the model of selfish routing. So what is a selfish routing pattern? Well, a selfish routing pattern is a pattern that takes all the agents from their corresponding origin to their corresponding destination, and such that no agent can reduce its cost by moving unilaterally to another option. And what I'm claiming here is that this routing, which I'm drawing here, is selfish routing, in the sense that no agent has any incentive in deviating to the alternative strategy. So in this case, both agents are incurring that travel time of 2 units of time. If they were to deviate to the other option, they would still incur the same amount of travel time. There is no incentive in deviating. And what I'm plotting here is actually a selfish routing allocation. That's good. So if this is clear, the next question we should ask ourselves is, well, how are we going to measure the quality of this allocation from the standpoint of society? So if we take about society, is this allocation here good or bad? And the idea is that we're going to utilize a cost function to measure whether this allocation is good or bad. And the most obvious cost function is that of summing the cost of all the agents, right? So basically computing the total travel time in the system, which in this case would amount to 2 plus 2, as both agents are incurring 2 units of time. That's good. So if this is clear, then we are asking the following question. Well, if we were this central operator, could we enforce a particular route to each and every car in order to minimize the system cost? So is there a better allocation from the standpoint of society? And the answer is yes. It's trivial to observe that if we send 2 cars on 2 different routes, the system cost would decrease. And in particular, in this specific case, the optimal cost would be 3, 2 plus 1. It's very simple to verify. So I'm going to utilize now a specific terminology, which I'm going to clarify. I'm going to formally define in a second. The idea here is that I'm going to think about this selfish allocation here as being inefficient. And I'm going to measure the level of inefficiency by looking at this ratio. I'm going to divide the system cost in the selfish allocation and the minimum system cost. So I'm going to say that this routing pattern here is 4/3 inefficient, 1.33 inefficient, if you wish. Clearly, the lower this number is, the closest we are to the optimal routing. And the question that we are interested in is that of congestion pricing. Remember the whole problem. So the question is, can we design congestion pricing so that we move away from this bad selfish allocation towards an allocation that is optimal or close to optimal? So the idea is we're going to introduce some congestion pricing, some toll in each and every edge, with the idea of moving away from this bad allocation and going to the good allocation. So I'm going to propose here a very simple and trivial tolling scheme. And the idea is that I'm going to toll agents proportionally to the congestion they impose. So if one agent imposes, when one agent is here, the toll would amount to 1 unit of money. When 2 agents are there, the toll would amount to 2 units of money. And the same for the other link. So I'm now asking the question, is this pattern here, again, a selfish routing when tolls are also taken into consideration? And I would assume it's not very difficult to see that this is not the case, right? When agents factor in both travel time and tolls, this is no longer a selfish routing allocation, because both agents would incur a travel time plus toll of 4. But if any agent was to deviate to the upper link, that agent would incur a total cost of 3. Right? So this is not a selfish routing. And in fact, you see that the only selfish routing here is exactly that exactly matches the optimal. So in a nutshell, what we've done here is that we've introduced toll, so that we've moved away from the bad selfish routing, and the selfish routing, when tolls were included, would coincide with the optimal route. If this is clear, then my presentation should be over, right? We thought about the level of inefficiency. We introduced a very simple mechanism, and this mechanism is optimal in the sense that the inefficiency, when tolls are introduced, completely goes away. Well, I mean, is this always the case, right? I mean, if I'm going to utilize this simple tolling scheme on a different network, maybe a more realistic network, would this work? Would it work for different origin destinations? Would it be robust against a number of variations, for example, mischaracterization of the travel time? So if this is not the answer, then what pieces of information do we want to utilize to design tolls? What are good pieces of information to utilize? So in some sense, I'm now ready to state the main question, which is that of designing, of computing optimal tolls. I'm being informal here, but the idea is fairly simple. We want to compute tolls that minimize the inefficiency as measured by this ratio, which I informally introduced before. It's 4 divided by 3. Okay. I'm gonna pause for 10-15 seconds to see if any of you has any question on the high level ideas here. After that, I'm gonna go through the mathematics, and the mathematics will really simply just be about putting some math and some formal definition behind each and every of these elements I've introduced here.
I do have a quick question.
Yeah.
So maybe I missed a detail there, but what information do each of the cars have? Because if I drive the red car, in order to make the optimal decision, I need to know what the blue car will do. So I guess there's some sort of need of coordination between them. And also in the bottom example, why don't we get the 2 arrows flipped? I guess it's a symmetric situation, right?
Right. Yeah. So I think you're asking a couple of questions at the same time. Thank you for that. So the first question is, how much information do the agents have when taking decision? Now here I'm thinking about a purely game theoretic setup. So the idea is that everyone has information about everything to begin with. And we are thinking about Nash equilibrium as an allocation that arises by every agent being infinitely rational, thinking very hard and doing the best, given that the other would also do their best. Obviously, you can then think about this being a very restrictive assumption. You can think about wanting to do this online. So you can think about learning procedure that would allow you to converge to a Nash equilibrium. Each agent might wake up, might revise his own decision based on the information about the congestion on the rest of the network and update his decision. But to make it very simple, it's purely static for now. And agents have information about everything. And I agree with you that it's non-realistic. That was one of the points being raised. The second question, I think I forgot that. What was that about?
It was just the bottom case, but I guess in that sort of setting, it also
it's anyway a good question, right? Because there could be an element of fairness. Right here, you're saying in this scenario we are sending the red agent on the top and the blue on the bottom, but we could be doing the other way around. Absolutely, that's definitely the case. So there is more than one optimal solution, and there could be fairness issues. Yes, I concur with that.
Right. Thank you.
Okay, unless anyone else, I'll move on. Okay, so I'm going to now introduce a general model for routing on a network, and the model I'm going to utilize is that of atomic congestion gain. The model is fairly simple. We just need very few elements, and the idea is that we're going to utilize a graph to model the underlying road traffic network. Nodes represent intersections, whereby edges represent roads. This is fairly standard. Now we're going to assume that there is a certain number of agents, in this case to simplify the red and the blue car, and each agent is interested in traveling from a certain origin node in the network to a certain destination node in the network. Now as a consequence of that, every agent has a number of options, which are all the possible paths that connect origin to destination without thinking about self-loop, for example. In this case, there are 2 options. Now, the last element I'm missing to fully define my problem is that of latency function. The latency function will tell me for each and every edge how long it takes me to travel through that edge. So I'm going to assume that I'm given latency function. I assume I know what the latency function is for each and every edge. And I'm going to assume that the latency, so the travel time through each and every edge, depends only on the number of people currently congesting that edge. This is a structural assumption in a sense, in that travel time on that road only depends on the congestion on that road and on nothing else in my network. And obviously, there is a latency function associated to each and every edge, right? This is a property of the edge. certain edge, for example, edge 1 would have latency 1, edge 5 would have latency 5. And I assume these are known to begin with, so my problem is well defined. Now, this notation, as for the notation, this notation simply means that the latency on edge E depends on the total congestion on edge E. So think about this, this notation as total congestion on that edge. Now, once I have these items, I can fully define my problem in that the agent costs are nothing but the travel time, right? As we've seen in the previous slide. So the travel time for an agent selecting a certain path is nothing but the sum of the latencies collected along the path from origin to destination, which is precisely what I'm writing here. While the system cost, as we introduced before, is the sum of the cost of all the agents, so the total travel time spent on the network. And I could have written this up as the sum of CIs, but I'm just writing here with a slightly different notation. But this is nothing but the sum of everyone's cost. Now, once I have this, I can start introducing formally the notions I introduced before. In particular, I'm going to look at the ratio between the system cost, the total travel time at an equilibrium at a selfish allocation, divided by the total system cost at the optimal allocation. And as we've seen before, this ratio here is larger than 1. I'm going to call this ratio inefficiency. And actually what we typically do in that we need to be robust against a number of variations is that we look at a worst case scenario over a certain given set of instances. So say we are given a certain number of instances, different graphs, for example, different possible origin destination demand, then we want to look at the worst case inefficiency in order to be robust. And now this is termed within the game theory community. This is referred to as the price of anarchy, in that it quantifies the inefficiency that arises from moving from centralized decision-making to distributed and selfish decision-making. Now here, as you've noticed, there is no toll whatsoever. This is the untold setup. No mechanism is utilized. So what do we want to do? Well, we want to introduce a tolling mechanism. That is, we want to introduce one toll per each and every edge. So think about adding edge 1 and adding to edge 1 toll 1, edge 2, say, and toll 2, and so on and so forth. Now, the key, one thing I want to remark here is that the toll we are adding is a tolling function, right? So this toll depends to begin with on the congestion. So for example, it could be the proportional tolling scheme we've seen before, just to clarify. And so the idea is to introduce tolls throughout your entire network so that the resulting equilibrium would move away from the bad equilibrium we had before and moves to a better equilibrium. So the overarching goal then would be, can we design tolls so that the cost at the equilibrium is the lowest possible, right? So that more formally, the price of anarchy, the ratio between these quantities is as close as possible to 1. And now I can state somehow my design question more formally. I do want to design tolls that minimize the price of anarchy. And this is almost formal. The only element I need to add to make this 100% formal is to tell you what set of instances is allowed. And I'm not going to do this for now. I'm going to do this in a couple of slides, but I hope this is sufficiently clear for now. Now, the question is, one of the questions we need to answer, which I sort of highlighted before, is, okay, we need to design tolls that minimize the price of anarchy. How much information are we going to utilize to compute these tolls? I'm going to distinguish here between two extremes. I'm going to distinguish between the full information setup and the local information setup. So in the full information setup, I assume that to compute one of these tolling functions, just one of them, I'm going to utilize full information about my instance, meaning origin, destination of all the agents, latency function over the entire network, and the entire network structure. So I'm going to throw this information in a complicated machinery, which is going to hack and pass and produce toll on edge 1. And I'm going to do this for each and every edge. On the other extreme, I'm going to be looking at the local information setup. Now, in the local information case, the tolling function corresponding to one road, to one edge, will only depend on the latency function on that edge and on nothing else. So think about going to ETH, just looking at the road in front there and computing the toll based on the travel time on that row. There are no other information about your entire network. So obviously this would be a much linear machine, but sort of to highlight the differences here, in principle, one would hope to extract much more performance when looking at the full information case, right? We are throwing in all these pieces of information, we should be getting something better. On the other hand, one might envision this being intractable because of the number of inputs that are required here to compute at all, as well as to be not robust, in the sense that any minor modification, even one single agent changing its destination, will significantly impact the tolling. We would have to recompute the total tolling. On the local information case, instead, we would be settling for less performance to begin with. We are not exploiting perhaps valuable information, though as we will see, this would be much simpler, perhaps tractable to compute, and would be robust against a number of variations. The network structure can change, the latency function on all the other edges can be mischaracterized, the agents can change their origin or destination, right? So I hope you appreciate the differences here. In one case, you get more performance, but most likely less robustness, and the other way around. Okay, now before presenting you the main result, I would like to walk you through a bit of history and related works so as to better position the result. So the model I introduced today is that of a classical atomic congestion game. This was introduced by Rosenthal about 50 years ago. Today I'm tailoring it specifically for road traffic problems, but there's a number of applications which are much broader and simpler road traffic. And in fact, all the results I'm going to talk about do apply to all these other setups. Now, one of the cornerstone elements after that has been the introduction of the notion of price of anarchy, which is this metric which we utilize for inefficiency. And this is thanks to these two well-known fellow computer scientists, Koutsapias and Papadimitriou. This was about 20 years ago. And after that, a number of well-known computer scientists work on the quantification problem, meaning given a certain model, for example, that of congestion game, can we quantify what is the price of anarchy? Can we quantify the inefficiency that arises from self-interested decision-making? There's a lot of work here in regard to quantification, though there is much less work in regard to optimization, which is what we're interested in today. We're interested in the optimization in that we don't want to know what is the price of anarchy. We want to design tools that achieve the lowest possible price of anarchy. And there is some work here, though I would say the closest result to what I'm going to talk about today is this work here by Paccagnan. It's a more recent work by Below, which I'm going to talk in depth later on. So having said that, hopefully the high-level picture is quite clear. I'm going to provide you with the main result. And I'm going to do so at sort of a high level. And then I'm going to utilize the rest of the presentation to sort of back up my statement. So the claim is the following. To the best of our knowledge, what I'm going to introduce you today is the first known solution that allows you to compute optimal tolls, meaning tolls that minimize the price of anarchy in congestion game. Now, the problem has been open for a number of years in that, since the introduction of the price of anarchy, a number of works have looked into how to compute tolls and minimize the price of anarchy. And our recent results show that surprisingly, you can do so through a tractable approach. And now I'm going to back up this claim in a second. Let me just sort of showcase what is the consequences of this. And I'm going to do this in the case of polynomial congestion games. So polynomial congestion games are a class of congestion games where your latency function, so the travel time, is a polynomial function in the congestion. And the reason for which they're studied is that typically a number of transportation scientists utilize polynomial functions to characterize the travel time as a function of the traffic, of the level of congestion. So how should we read this table? So to begin with, on the left of these double lines here are existing results in the literature, while on the right it would be new results due to our recent work. So you should read this table in the following way. When D is equal to 1, so for example, for a fine congestion game, so for congestion game where the latency function are only a fine function and not of higher degree, and we know that the price of anarchy when no tolls are there, so the inefficiency when no tolls are there is 2.5, for example. When quadratic functions are utilized, it's 9.5, and so on and so forth. Now, what does this mean? For example, this 2.5 means the following: no matter what instance we are given, the cost at a Nash equilibrium will never be higher than 2.5 times the cost of the optimum. Now, these are existing results in the literature due to some of the works you see here, mainly Christodoulou Koutsapia, Strafgarden, and Alain. Now, our approach not only allows to compute optimal tolls, but also allows to compute the price of anarchy for the untold setup in a number of setups. As a matter of fact, we recover all these results and a number of others by simply solving one linear program for each of these cases. So we're gonna be able to recover all of the known results that are listed here. And other than that, we're gonna compare our results with tolls that are based on global information. So these are the complicated machinery that takes into everything and computes a toll. So these are known results that are typically negative results due to this work here. These are negative results that tell us the following: no matter how much information we have about the system, we'll never ever be able to reduce the price of anarchy from 2.5 to a value that is lower than 2, for example, for affine, and similarly for all the others. Now, instead, we are interested in computing local tolls, which is what I'm going to show you here. So this is what comes out if you solve the corresponding linear program for linear tolls in the case of affine congestion games. So as you can see, the idea is that you're going to be able to design local tolls that are going to be much more robust in that, they're going to be agnostic to a number of elements in your instance, and they substantially achieve the lower bound you can see here. So for example, there is less than 1% performance degradation here, but you go from global and most likely untractable to local and tractable, meaning computationally, meaning that we are going to be able to compute this in polynomial time. Now, this is when we look at optimal local tolls. We can also take one step further. We can look at optimal tolls that are even congestion independent. So there is you don't need to measure congestion and then broad tolls. It's simply a constant that is congestion independent. And now what you obtain here is that there's some level of degradation, if you want to think about it, going from full information local to local and even constant, but the level of degradation is very limited, at the very least for low order polynomials. So the sort of the bottom line here that you should take home is that optimal local tolls are almost as good as global tolls, which are most likely difficult to compute, and even constant tolls don't lose too much performance. Now, as I said, this is an application of the main machinery, which is what is contained in this main result. So the rest of the talk would be about proving you the main result, and this would then look like an exercise at the end. I'm going to pause again for other 10-15 seconds to see if there's any question on sort of the results and the connection within each other.
Dario, can I ask a small question?
Sure.
Thanks. So I was wondering, the lower bound doesn't mean that, so does it mean that global design of tolls exists, or is it just an impossibility that is not possible to go below 2?
Yeah, it's a very, very good question. So for some of the cases, it is both. For some of the cases, not. So for example, in the affine case, this is both a negative result and there is a polynomial way of computing that. For the others, I have not seen any, but it could be, we could even think of this as being sort of the limit you can obtain even by a polynomial algorithm. But even if that was the case, right? I mean, to compute this, you would need a lot of centralized information, and you would basically be able to achieve the same with very limited information. And sort of what you should bear in mind here is that once one agent changes the destination, you would have to recompute this whole machinery again, right? While here you wouldn't have to do anything. I don't know if I was clear. If I wasn't, please ask me again.
Sure. No, I think it was clear. Thanks.
Okay, if no one else, if this is reasonably clear to everyone, I'm gonna move on and then sort of try to put a bit of meat behind this claim. Okay. So the structure of the presentation now is the following. We have 3 items which we need to go through. Item number 2 would be the sort of most mathematically demanding element. Point number 3 is very simple. So please bear with me once we go through 1, in particular 2. The first point is the following. We are going to prove that optimal mechanisms are linear. Are linear in some sense, meaning they are linear maps from the set of latencies to the set of tolls. This does not mean that the optimal tolls are linear function in the congestion. And I'm going to clarify this in a second. So the first point is about proving that optimal mechanisms are linear maps from two infinitely dimensional spaces of functions. Okay. Once we have that, we're going to take a step back. We're going to try to characterize the performance of a given linear tolling mechanism. So assume someone gives us a linear tolling mechanism. Can we tell you what is the corresponding price of anarchy? And this is going to be the crux of the mathematical argument. At the end of the day, point number 3 would be about putting these two elements together, these two results together. We're going to utilize the linear program we derived here. We're going to modify that linear program. We're going to search over all the possible linear tolling mechanisms and compute the optimal linear tolling mechanism, which would also be optimal over non-linear mechanisms because of point number 1. I hope this is clear. If not, feel free to interrupt. So we're now going to go through 1, 2, and 3. So the first element, the first claim is that optimal tolling mechanisms are linear maps. And to state the claim, I just need to clarify what is the set of allowable instances here, which is the only element that I'm missing other than everything else which was fully defined before. So this is typical in the literature, actually more general than what is typically done in the literature. I'm going to assume that any possible graph is fine. So the instances will contain all possible graphs you can imagine. They would contain all possible origin-destination pairs such that I can draw a path from origin to destination within the graph, and would allow for any possible number of agents, which is upper bounded by n. In reality, we're going to take the limit as n goes to infinity at some point. So basically, so far, there is no restriction on what instance. The only restriction on the instance comes in a second, and it's about what latency functions are allowed. So we're going to assume, just follow me here, please. We're going to assume that all latency functions belong to a common set of functions. And the assumption is that this common set of functions is obtained by the linear combination of some non-negative coefficients times some basis function. So for example, the polynomial congestion gain is simply obtained by utilizing 1x, x to the power of 2, and all the polynomial bases here. But you can obviously generate much more than that. And to make it simple, we're going to assume for now that the number of bases here is fine. Okay, so m is given is fine. So what I'm going to do, I'm going to stack all these bases together in a set of functions, which I'm going to call capital B, containing B1, B2, B3, Bn. So this is the only restriction I'm going to put in the set of instances. And as for the tolling scheme, let me just remind you that we're going to utilize a local tolling scheme. Now, let me clarify on what this mechanism does. So LE is a latency function. So this object here is a function. This object here is a function. This is the tolling function. So this object here maps a function into another function. If you wish, this capital T here, if you want to call it like that, it's a function, right? You're mapping a set of functions into a set of functions. Just want to make this clear. Once a mechanism is given, a number of agents is given, and all the possible bases are given, the price of anarchy is going to depend only on those elements and on nothing else. The problem is entirely defined. And now I can finally state my claim that I have enough tools now. The claim is the following. I claim that there exists a local optimal tolling mechanism that is linear. There exists does not mean that all of them. So there exists one, at least there exists one that is local and is optimal. Sorry, it is local, optimal, and is linear. So what do I mean with this statement? I mean the following. I mean that there exists a tolling mechanism such that when I apply the mechanism to one of my latency functions, this is exactly equal, and the claim is this equality here, is exactly equal to taking the linear combination of the same coefficients I was beginning with the toll applied merely to the basis function. Right? So if I want to compute the tolling function for a complex latency function, well, let me just take a step back. Let me just compute the toll on the basis and put them all together. So So this basically means that instead of computing something that is infinite dimensional, meaning the optimal mechanism here for all the possible latencies, now we can compute the optimal mechanism only on the latency on the basis function. So if I have n basis function, I need to compute t opt b1, t opt b2, and so on and so forth. And after that, I will be able to recombine them to obtain an optimal local mechanism. Is this clear? If not, please feel free to interrupt or ask any question. Okay, I assume it is. So once and I'm not going to prove the statement, you're welcome to ask me at the end of the presentation on how we're going to prove the statement. I will not have time to go through that, but let's take this as a sort of given. The next step is, as I said before, to take a step back and think about being given a local mechanism. So now we are given a local mechanism, a local linear mechanism. How can we compute the price of anarchy? And this is the core technical result, which is going to be in the next slide. So I'm going to assume the problem is given. I'm going to assume the tolling mechanism is given and is linear. And I'm going to form this function here just for ease of notation. So I'm going to sum the basis function plus the toll applied to the basis function. Just note here, I'm summing functions to functions. So this fj is a function, the function of the congestion level. Okay. Now I claim that the price of anarchy has a certain value, and I claim that this value is 1 divided by c star, where c star is the value of a tractable linear program. Now, the linear program is as follows. We are maximizing one of the decision variables, and there are 2 scalar decision variables only here, nu and rho. And I'm maximizing this rho subject to a number of constraints. It is not important that you parse the constraints. It is important that you believe me they are linear. So how should we read these constraints? So for every basis function j, we get 1 constraint. So we're going to have a number of constraints, 1 per each basis. To simplify for now, let us think we have 1 basis only. Okay, then how many constraints do we need to verify? We need to ensure that a constraint is satisfied per each tuple xyz. So xyz are given tuple of integer numbers, and these are all the possible integers that live between the positive orthants and the simplex of dimension n. So as you can see, there are order n cube integers here. For each of these integer points, say 0, 0, 1, this will correspond to x equal to 0, y equal to 0, z equal to 1. We take these numbers, we plug them in here, and we get a linear constraint. Because once we evaluate this in x plus z, this is going to be a constant, this is going to be a constant, and this is also going to be a constant, right? So this is going to be a linear constraint in rho and nu. And we have how many constraints? Well, we have order n cube constraints, because the number of points within this region here is order n cube. In reality, you can get away with less, you can reduce to n squared, but it's not really important here. The main point is that if you want to compute the inefficiency of a given tolling mechanism, you should solve this linear program, and this linear program is tractable in that it has 2 decision variables and order n cube times m, if you wish, constraints, so polynomially many constraints. This is the key mathematical result. If this is clear, if the main point here is clear, then it's going to be just about putting the 2 elements together. I'm going to again pause for a few seconds to see if anyone comes up with a question. Okay, just a final comment here. Solving this problem not only gives you the exact price of anarchy, but also gives you the worst case instance. So it builds for you automatically the worst case instance achieving that price of anarchy. And let me just comment on the fact that if you want to achieve all those results I've listed before in the untold case, you simply need to set t equal to 0. So there's no toll is set. So then fj is equal to simply bj, and just solve this linear program with your corresponding basis functions, for example, polynomials, to reobtain the table we've seen before. Okay, now putting together the 2 things, we get the optimal design that I was mentioning as the main result. I'm calling this a theorem, but it should be a corollary, to be honest. The idea is that we're just putting together the building blocks I introduced before. So here I'm saying, let me give you a problem. Let's assume the problem is given. So the basis function are given. I need to design an optimal local toll. How do I do that? Well, I'm claiming that I can compute an optimal local toll by the linear combination of the coefficients. I was starting with the coefficients defining the latency function times the optimal mechanism applied to the basis. So now the only thing I need to tell you is what is the optimal mechanism applied to the basis. And I'm telling you, take this as the difference between these two functions. This we know what it is, whereby fj opt comes out from the solution of this additional linear program. How do we obtain this? It's fairly simple. We look at the linear program to compute the price of anarchy. We simply allow for the tools to be a new decision variable. We do a little bit of reworking, and that's exactly the linear program we get now. So this linear program is also optimizing over linear toll, over linear local tolling mechanism, where these constraints here are again one per each and every x, y, z, as you've seen before. Now, if you don't want to know anything about the talk, if you didn't understand anything, the only thing you need to keep in mind is this block you see here. So we are given a latency function per each and every edge, and we need to compute the optimal toll. How do we do that? The optimal tolling function. So we think about this latency function as coming from the linear combination of some coefficients and some basis function. For each of these bases, we solve one single linear program. Note that there is a decoupling argument here. So for each basis, we solve one linear program. We've computed the optimal toll applied to that basis, and we just again do the linear combination again and obtain the optimal tolling function. Okay, hopefully this is clear. We've coded this up in MATLAB as well as Python, so you can find this in GitHub if you're interested in playing with optimal tolls. You're more than welcome to have a look at that. Having said that, I'm gonna quickly go through a summary of results and opportunities and then conclude. So what have we looked at today? We've looked at socio-technical systems. We look at designing, incentivizing good performance in socio-technical systems. In particular, we looked at road traffic routing, and we used atomic congestion games as a model of that. To the best of my knowledge, this is the first result that allows you to design optimal tolls in congestion games, optimal in the sense that minimize the price of anarchy, and in the sense they are local. We've seen how computing and optimizing efficiency is surprisingly a linear program, which is tractable. I would have imagined some form of combinatorial optimization problem arising from there. And in addition to that, we've seen a number of consequences in that we recover generalized existing results. We've seen how local information is almost as good as full information. We've also seen as even a local and constant tolls don't do too bad compared to the centralized global solution. And there's clearly a number of opportunities in that the framework is very much unexplored, but I do not think I have time to go through this. If you're interested in the result, you can have a look at the following paper. This is where substantially all the results I talked about today are present, even though some of the ideas, preliminary ideas, were developed in this other manuscript here. Having said that, I'd like to spend the last minute on sort of summarizing some of my research ideas, research directions, and outlook. So in a broader sense, the goal is that of coordinating socio-technical systems to desirable behavior. We've seen today road traffic routing, though I believe there's interest, the problem that we should look at is much broader. For example, multimodal transportation systems are systems that have been particularly studied lately. So one of the questions I'm interested in is, can we lay the foundations of congestion pricing in these setups where there are different layers, where different rules need to be satisfied within each and every layer? Obviously, all that you've seen today, a very simple critique to all you've seen today is that all the results represented are worst case. So you might be asking the question of, well, maybe we might have information in terms of data, in terms of perhaps origin, destination, the network structure, and so on and so forth. So can we look at a data-driven approach to that? That's definitely a very good question that I'm interested in. Finally, just a word of caution in that there could be fundamental trade-offs that arise here. For example, designing in order to improve the worst case performance might have consequences on the best case performance or perhaps on the average performance. This is something that I'm particularly interested in. Finally, most of what I've talked today actually, to some extent, can be carried over to engineered systems, though I would like to leave it here so as to make it as brief as possible. Finally, I would like to let you know that very recently there's been an opening within my group at Imperial College. So if you know anyone interested, or if you are yourself interested, please feel free to circulate this piece of information and put them in touch with me. Having said that, I would like to thank everyone for the attention, and I'll be more than happy to take any question and just stay here for a casual chat. Thank you, everyone.
Thank you very much, Dario. Very interesting talk. Are there any questions from the audience?
I actually have a question, if I can.
Sure.
So, thanks, Dario, for the nice and clear talk. I was curious. So basically, your pervasive anarchy results are like bounds are hold against any network topology, right? And
correct.
I guess it's much maybe more intricate the analysis if you are given a given network. Have you tried doing also like following maybe similar steps for that case, or do you have some negative results in that sense?
It's a very good question. So I do not have an answer to the question, in that I completely concur with everything you said, in that the analysis I presented today heavily relies on the fact that you are allowed somehow to construct whatever instance you want. So, it's network agnostic. If we now start putting constraints on what networks you're allowed to search over, in looking for the worst case scenario, it becomes much more difficult. And I believe very little of what I said today would carry over in that setup. It is a very relevant question that I'm thinking about and pursuing myself, in that the price of anarchy results that we've seen here, they're worst case, right? But then you might, almost always you have information about the networks. How do you incorporate that?
Yeah.
It's extremely interesting, but I think it's also very, very challenging.
I see.
At least this has been my experience in trying to think about the problem. Maybe you have some ideas yourself, and I'd be more than happy to chat.
Okay, yeah, sure. Because maybe also related to that, I remember like in the first slides, it was interesting to see like and I think maybe it's your ultimate goal, the feedback loop with the mechanism design. So I was wondering in this specific application, what could be a feedback loop that you will maybe can use to update your pricing? Maybe after a day or more, you're gonna change your pricing based on some information. And what could be some?
Yeah, so
what,
I think
what like those information can be. I guess little functions. Yeah, I was wondering like what information can you use to improve the pricing if you knew more about the game.
So in principle, at least the way I'm thinking about it as of now is that I'm thinking about two types of information. I'm thinking at let's say real-time information. So for example, congestion. So if you think about the results that we have in what I presented today, your toll is going to depend on the congestion level, right? So if I'm able to measure congestion now, then I'm going to measure congestion and give you a toll that is congestion dependent. So for example, in the morning, it's more expensive to go in this road. In the afternoon, it's going to be cheaper, just to make it very simple.
Mm-hmm.
But there is another level of sort of information you can exploit, which are a priori information, for example, right? You might have ideas on the traffic pattern. So for example, the origin destination is typically distributed in a certain way, or your typical underlying network structure follows a certain topology. Though incorporating this is typically more challenging, and that's I think where your question lies. So I think all the possible types of information can be encoded, but how do you do it in an efficient way? It's at least to me one of the interesting questions to ask. And you can range from sort of more data-driven approaches, where you think you have past instances about what happened, to sort of still worst-case analysis, but for restricted cases of problems, as you were saying. Maybe I have an idea about the network, so I want to do worst-case analysis, but given 5, 6, 10 networks configuration, I'm allowed to use, and no more than that.
Mm-hmm. Thanks.
Okay, I have a question.
Sure.
I joined a little late, so I'm sorry about that. Maybe you already commented on what I'm about to ask. But what are the scales of the toll? Like, this is maybe a perhaps more fundamental question about tolling in general. But how do you match the scale of delays to that of tolls, which would be, for example, money?
So you are saying you add money to time. How do you put it together?
Sorry?
You're asking the following question. You are saying you are summing time to money. How do you sum the two together? Right?
Yes.
Is that the question?
Yes.
Okay. It's a very good question, which allows me to elaborate a bit on that. So what we've done today, it's simply summing travel time and money, as you've seen perhaps early in the slides. And I've not talked about this, so don't worry, your question was not already answered. There's one key assumption which you need for that, meaning that all agents have the same sensitivity. Meaning you can think about utilizing a single function to measure the agent's well-being, and as long as the agents have the same sensitivity for time and money, then you can do that. Even if I were to put a coefficient in front of the formulas that I had before, everything would work out. So I can do something like travel time plus alpha money. That's fine, as long as the alpha is the same for everyone. Now, if you start thinking about a model where agents have different sensitivities, so with this alpha parameter is a function of the agent, so alpha, maybe you have a distribution of that, then it becomes, well, everything that I've said here does not go through, it becomes much more challenging. One thing you can do though, still utilizing the same techniques that I talked about today, is you can split up the agents in sensitivities, let's say boxes. So let's say that we have a number of discrete regions. Perhaps there are agents with high sensitivity, medium sensitivity, and low sensitivity. If this is the case, then the machinery I talked about today can still be reapplied with a little bit of bells and whistles here and there. But in principle, I wouldn't know how to treat the problem. There's a lot of study precisely in the model you were mentioning, that with sensitivity, where the sensitivity follows a given distribution. But even computing just computing an equilibrium configuration in that setup is very challenging. And so computing tolls and thinking about doing tolling design is extremely, even more challenging.
Thank you. One suggestion perhaps is to maybe not use money, but rather like some sort of tokens that are just restricted to this system.
Something like karma, something like karma, right?
Yes. Yeah, exactly. That would have been what I would have said. In fact, Joelle, we've been thinking about doing this with karma. So if Eza or Joelle are interested, we can talk more about that.
Okay, cool.
All right, other questions? If you have other questions, I think Dario gave his contact information to reach him. But if there are no other questions, I will call it a talk. Thank you very much, Dario. I will send you the video once it's produced.
Yeah, thank you everyone. As I said, I'm gonna stick around for perhaps 5-10 more minutes to see if anyone has some other follow-up question or anything.
Thank you very much. Bye-bye, see you next week, guys.
Thank you.